Hi, Ibrahim. Welcome to the podcast.
Yeah, hi Robin. Yeah, thank you for having me.
Brilliant. Let's begin with where you work and what you do.
Yeah, um, yeah. My name is Ibrahim, and I'm a senior AI research engineer, leading the team at Kigali. Yeah, I work for InstaDeep, and yeah, my team is focused mainly on the AI for social good projects that we do at InstaDeep. So yeah, the main thing that's brought us here today, which is one of the projects that we've been working on, which is InstaGeo.
Brilliant. Why don't you tell us a little bit about that then?
Yeah, maybe just a couple of steps back to talk about history. So in the year 2019 slash 2020, there was a major locust plague that affected some uh, parts of the Horn of Africa and some parts of Asia. It was a serious outbreak. And at that time, when we realized it in my company, we were like, okay, how can we leverage our expertise in AI to address this kind of challenges so that it doesn't reoccur like in the future, or if it does, the impact is minimal.
Hmm.
So then we jumped onto it and started looking into it, reading a lot of literature work around ecological modeling and locust research. And then, yeah, that was basically how we started.
Hmm.
And because we wanted to build a tool that was going to be free for researchers as well as practitioners to use, we realized that from the onset, we also needed to make sure that the data we consume, the tools we consume that we use to consume the data and build the software is also free to use.
Hmm.
And interestingly, there's a lot of free and open source geospatial data, especially multispectral data from the
Mm.
likes of Sentinel-2, Landsat 8, HLS, and then the like of that. And this kind of data, like I said, they are free and open to use. They have tremendous use, I would say. So, but we realized something very critical, which was that this data is free to use, and a couple of researchers have also built what we call foundational models around this data. So by
Mm.
foundational model, we mean they take the data and then they train very big models that learn in an unsupervised way, try to understand the data so that those models at the end of the day can be easily fine-tuned for different downstream tasks.
Hmm.
Now, what we found is that the data is there free to use. The models, foundational models are also there free to use, but there is something missing in between,
Mm.
which is that there is, at least at the time when we realized this, there's no free tool that allows you to take the raw Sentinel-2 data or Landsat 8 data and produce the same data that you will feed into just your special machine learning models.
Okay.
And interestingly, all the researchers that also like release their model code for the geospatial machine learning model and say, yeah, you can fine tune it for various downstream tasks, no one also releases the code, the data pipeline code that was used to generate the data that was used to train the model.
Mm.
So what that now means is that we have this geospatial machine learning model. We also have the free data, but you can't really put it to use except you invest a lot of time, a lot of effort,
Mm.
and you have the technical expertise to be able to like move from having that free open source raw data to a model ready data that can be used for training and inference. So
Hmm.
this is sort of like how we started and then the challenge we realized.
Right. So you were kind of under time pressure. There's this locust outbreak. You want to make a tool anybody can, look, use models to find out where these locusts are affecting, etc. You've seen that the data's out there, the models are out there, but it's not in a usable format. So you need to build some tooling to address that.
Yeah, although we actually realized this after a lot of work. So the first step that we did when we started looking into the locust breeding ground problem was to research like what are the techniques that researchers are using to understand locust habitat and their breeding mechanism. And then we looked into the literature around what is called ecological niche modeling,
Mm,
where we tried some classical machine learning algorithms, and we tried some approaches to do what is called absence data, pseudo absence data sampling. And then we moved from there to building a model that basically took variables, different environmental and climatic variables like temperature, pressure, soil moisture content, humidity level,
mm,
precipitation rate. So we took all of those low-level variables, we put them together, and then we fed it to our model. So that was the
mhm,
second stage of the work that we did.
mhm,
And yeah, we also published a paper on that. And then when we finished the second stage, then that was when we realized the first challenge that we had, which was that we built the model, but it's not we cannot operationalize the model. So by operationalization, I mean we cannot put it into everyday use because the data that we used was created by aggregating different variables from different sources.
mm,
And those variables, they are not all available when you need them. So for example, if you need to make inference today, you may realize that a couple of them are not available, or if yeah, it's very hard in any case like to assemble like all the different sources at at the given time, because some of them they release them like after some period of time. So we started looking into, okay, this is a challenge, and we don't want to just do research and publish paper, but rather we want to have real impact on the ground. So
mm,
this was what informed our decision to look into multispectral data, because
mm,
we saw that multispectral data, especially the HLS archive, which was a harmonization between Sentinel-2 and Landsat 8, is available every 3 to 5 days. So
mm,
that meant that we can easily get data anytime we need it.
mm,
So uh, so the question now at that time was, we've seen that multispectral data is useful for a lot of use cases like land cover mapping, crop classification, and the likes.
mm,
But can we use it for identifying locust breeding grounds? That was the first hypothesis that we came up with.
mm,
And interestingly, when we tested that, we found that yes, you can actually use multispectral data to identify locust breeding grounds, and that was a very great moment for us. We actually
mm,
published our finding. Then after that, that was when we now realized the initial thing I said, which was that there's a disconnect between the multispectral data and the geospatial foundational models.
mm,
So the effort it took us to build our first geospatial data pipeline that takes raw multispectral data and convert it to model-ready format. Once we completed this and realized that, look, this is not a trivial thing, and we are sure that a lot of people will not be able to do this,
mhm,
then we decided to say, okay, let's put things together and create a tool that allows researchers and practitioners to leverage this open source multispectral data for any use case, because we've realized that this data has a lot of use cases.
mhm,
But then these are some of the bottlenecks, like I mentioned. So that was how we started building InstaGeO.
mhm.
Yeah.
Good. Can I just also clarify, was it foundational models in particular that you thought were challenging, or just any model, and you decided foundational models were where you would focus?
The good thing about the foundational models is that because they've already been pre-trained on a lot of data, so you can easily gear them for your downstream task of interest.
Mm,
That was the motivation to actually lean towards geospatial foundational models. And also, one of the work that also inspired our decision on geospatial foundational models is the work that the collaboration between NASA and the IBM research team, where they created a family of geospatial foundational models called Prithvi. So they
Mhm.
released version 1 of Prithvi. They also released version 2 of Prithvi. So like if you look at InstaGeo, if you look at our repo, you'll see that we've mostly relied on the Prithvi family of models to
Mhm.
actually derive our own models, which we use for on different downstream tasks.
Right. And they were one of the first sort of foundational models that were published.
Uh, you mean the first foundational model was published in the space of
Well, there was
geospatial
a lot of
foundational
them,
models?
but Prithvi got a lot of attention when it was announced, I think.
Yes,
And that also
yes,
was
actually,
pre-trained on the HLS, I think. So that's
yes, it was pre-trained
aligns
on
with
HLS.
what you wanted. Right. Okay. Brilliant. So you've identified the models, you've identified the source. How effective was the solution for the locust breeding ground detection then?
Yeah, so the first thing that we did was that we tried to replicate the result that we got earlier with our new pipeline. And yeah, we got a very interesting result. Like we were able to replicate it and even improve on the result. And currently at the moment, we are now looking into like having uh, on the ground impact because the first thing for this kind of task is for you to build the model, then you assess it on the ground, and that's actually the very difficult part.
Mm,
So for this we are actually talking to some partners who are already like involved in the field work to see how we can collaborate to actually assess it on the ground because
mm,
there's a limit to what we can do as researchers, so we need to also like collaborate with other players.
of course. And what were some of the particular challenges there?
So early on, when we started looking into the problem, we tried to do the research and then at the same time, like get the model to be used by people in the field. But it turns out that the logistical there's a lot of logistical challenge around this,
Mm,
like collaborating with people like different organizations. You need to first find, a common interest, and then from there, like, so it's been difficult, and it's one thing that we've actually realized that it sounds trivial, but at the same time, it's
mm.
not easy.
Right. So
Yeah.
these are organizations that had individuals going out, making maps of, where these breeding grounds are
Yes.
occurring, capturing the data, sharing that
And
with you
yeah,
somehow.
I must stress that when we started the work on Locust, we actually uh, we looked into the organizations to partner with, and then we saw that the UN Food and Agriculture Organization has been doing a lot of work in this regard over a lot of years ago. So they were a natural first partner. So we reached out to them, and then we started partnering with them. We talked to like a lot of professionals from FAO, and yeah, we got a lot of insight. We got a lot of yeah, insights and guide on how to use the data because the ground truth data that we use comes from the FAO archive. That
Mhm,
yeah, it's called the Locust Locust. I forgot the name, but Locust something is the name of the archive that contains
mhm,
the data.
mhm,
And also for the on-the-ground assessment, they are also our first partner to actually talk to. And yeah, we've already the talks is already ongoing because they have access also to the different countries where this locust plague usually occur, and then they already have a kind of system, or let me say a network in place of different players within
mhm,
the field. But just to mention that Locust was actually our first pioneer project,
mhm,
but we've since expanded to even other projects.
mhm,
So like damage assessment, uh, uh, air quality assessment, which is
mhm,
also called aerosol optical depth estimation,
mhm,
then biomass estimation as well. Because the good thing, like I said earlier about multispectral data, is that it has a lot of use cases.
mhm,
So we built one tool that can be used to solve any problem that is possible to be solved using this multispectral data.
mhm. Right. So that's what InstaDeep is. It is the tooling that you need
Yeah,
to address all
InstaGeo.
these different address these
Yeah.
different challenges. And so the model is trained, you're happy with its performance. How have you been deploying that and putting that in the hands of, the communities that need that information?
Hmm. Yeah, before I go into that, let me first give a high-level picture of what the framework looks like. So InstaGeo is an end-to-end geospatial machine learning framework that makes it very easy for researchers, practitioners to go from raw multispectral data to an operational model. That's the goal. And it has three core components. The first component is the data component. So this does the heavy lifting of taking the raw, uh, basically not only taking the raw satellite data, all you feed to the data component is geolocation, so a pair of longitude and latitude, date, and label
Mm.
information. And that's all it needs. You can
Mhm.
also feed in raster. And then once you give it that and you configure like the different parameters of the pipeline, it will go to the HLS archive or Sentinel-2 archive or Sentinel-1 archive, depending on the one you choose. It will fetch all the corresponding granules, put them together if you have a
Mhm.
temporal data, and then crop the region that is necessary. And then at the end of the day, it gives you what we call chips in the shape that you specified. So for example, if I requested for 6 bands with 3 time steps and spatial size of 224 by 224, at the end of the day, it will give me a TIFF file that has a shape of 3 by 6 by 224 by 224. So this data in this format is now ready for, and also it's paired with the label,
Mm.
which in our case is a segmentation map of
Mhm.
size 224 by 224. And then you can then feed this to a model. So this goes to the next component, which is the model component. And this
Mhm.
component serves to basically fine-tune a geospatial machine learning model or train one from scratch.
Mhm.
So, and at the same time, you can also do inference after you have a trained model. So then you can take the data from the data component, you use it in the model component, and then you drive you have a model checkpoint.
Mhm.
Then we have the other component, which is the application component. Now, in this application component, you can take your inference, your predicted files, basically. So because after you perform inference, you save a GOT file, and then you can visualize it in the app component. So basically, it will overlay everything on an interactive map, and then you're able to visualize it. So
Mhm.
this was our version 0, I would say, the first version that we released. But since then, we released it actually in 2024. But since
Mhm.
then, we've made a lot of improvement.
Mhm.
So, like 2 weeks ago, we released a new version whereby in the data component now, because formerly in the data component, we usually pull the entire granule, which is very big. It has spatial size of 3660 by 3660 pixel.
Mhm.
We pull this and then we do like all the processing. So for example, we realize if you want to create a data set that is just uh, that will end up being 225 gigabyte, for example, you may end up pulling raw satellite data of like 1 terabyte. So this was not scalable for us. So now in the new version, what we've done is to leverage the STAC API,
Mm.
which allows us to basically use cloud optimized GeoTIFF to only fetch the region of interest from each of those granules. And now
Mhm.
our pipeline is very fast. Like
Right.
you can ask it to create like all the chips covering the entire Africa continent, for example.
Mm.
And then you give that to it and just wait for it to give you the result. So it's very
Right.
easy to use and very fast.
And it's
Then in the
quite
model,
modular as well, because you could change your stack catalog, use a different one, but still use the processing. You could take your TIFFs and put them somewhere else if you want.
exactly,
Ah, nice.
exactly. You got it. You got it. You
Yeah.
got it. Then in the model component as well, we've tried to make our models very lightweight. So
Mm.
like we do compression and then we track the carbon emission of our model as well as the computational complexity.
Mm.
So we have what we call a technique we call task-specific distillation, whereby we create a final model that corresponds to the difficulty of the task. So this
Hmm.
helps us to have like lightweight models, because remember that the goal is for us to be able to operationalize the model so that people can do like continental scale inference. So we need something that is lightweight at the same time with good performance.
Right.
Then in the first version of the app component, you needed to first do inference with the model component, then you save the prediction geotiffs, then you can then load them in the apps component and visualize it on the map.
Hmm.
But now, in the new version of our apps component, it's actually a full stack application built with the React framework. And then it combines or it joins together the data component, the model component, and then the app component itself. So
Hmm.
now if you go to instageo.io, you are able to draw a an area of interest on the map, select some few parameters to for the pipeline, for the data pipeline.
Hmm.
Then you click on the run job. And okay, you also select like the model. We have a couple of models
Hmm.
in our model registry. So you select the model of interest after selecting your area of interest, and then you click on run job.
Hmm.
And then it will go through the entire process. So it will fetch the data set, create the data in a model ready format, do inference, and visualize the result on the map, and also give you some analytics that you
Hmm.
can download and save as a PDF file. So
Brilliant.
that's the current state of what we have.
Well, congratulations. It sounds very fully featured, and it's obviously been the outcome of a awful lot of work. I'm wondering
Thank
what
you.
you still feel is left to do.
Yeah, I think for us, what is left to do is to have the actual impact on the ground. And like I said, this is another uh, this is an entirely different process. We need to reach out to partners and see how we can leverage this open source tool that we've created to really have impact on the ground across different sectors, I would say. Yeah.
Hmm. Right. So you want to see it out there being used as widely as possible. Um, Very exciting stuff. The code itself is on GitHub. That's open for everybody. We're going to do a separate
Yes.
video to have a look at InstaGeo and just walk through some of those features. I'll wrap this one up there. Just finally, so obviously you can go to GitHub and follow the activities. Do you post updates on LinkedIn or elsewhere?
Yes, and on the website also we have a feedback form for people to leave us feedback, and you can also create issues on GitHub,
Mhm.
and yeah, we'll be ready to take a look at any issue that anyone has.
Brilliant. Okay. Well, I'll leave all the links in the show notes. Once again, been a
All right.
pleasure. Until next time, take care.
Thank you. Bye.